Thanks. Go ahead.
Hi everyone, my name is Alireza Farhadi and my talk is about online bipartite matching with reusable resources. This is based on a joint work with Sivan, Delong, Niazadeh, and Balasubramanian. The problem that we consider in our work is a generalization of online bipartite matching. In online bipartite matching, the input is a graph G, and the G has two parts, V and U. And we call vertices in V offline vertices, and they are known to the algorithm in advance. However, vertices in U are online vertices, and they arrive one at a time. And they also arrive in an adversarial order. And whenever a vertex, an online vertex J arrives, it arrives with all of its incident edges. And at this point, the algorithm should either leave J unmatched, or it should irrevocably match J to one of the offline vertices, and it can't change that decision later. So this problem, it is known that to have a lot of applications. For example, it can be used in market algorithms. Specifically, suppose that we want to match search queries to advertisers. That problem can be modeled using online bipartite matching, and it is one of the most important applications of that problem. In our work, we however study a generalization of that problem, and we study online bipartite matching with reusable resources. Like the non-reusable case, the input in our problem is a graph G with two parts V and U. The vertices in U are online vertices, and they arrive in an adversarial order, one at a time. However, the vertices in V are offline vertices, and they are also reusable. That means that whenever our algorithm matches an offline vertex I will become available again after the time steps. In other words, if we match vertex I to an online vertex J, I will be available again when the online vertex J plus D arrives. And this problem also has a lot of applications. For example, it can be used for assigning virtual machines to customers in cloud computing platforms. And it can also be used to find an efficient allocation between houses and customers in rental housing markets. And another application of this problem is in allocating medical resources. For example, suppose that in a hospital, we want to allocate medical resources to patients. And we have some options like beds, ICU units, and ventilators to assign to each patient. And based on the experiment, we know that when we allocate a resource, that resource will become available again after a predictable amount of time. So in that sense, the resources in a hospital are reusable, and we can model that using our problem. So for that problem, we designed a competitive algorithm for online bipartite matching with reusable resources. The competitive ratio of an online algorithm is the minimum of the expected output of the algorithm, the ratio between the expected output of the algorithm and the optimal solution for the worst input graph. And we also assume that the input is non-adaptive. That means that the input graph and the arrival order of online vertices should be fixed in advance by the adversary, and the adversary can't change those based on the output of the algorithm. So for this problem, it is known that the greedy algorithm achieves half competitive ratio, and the greedy algorithm basically, after arrival of any online vertex, it matches that online vertex to an arbitrary available offline vertex. And that simple algorithm achieves half competitive ratio. So the question is whether we can beat the half approximation for this problem. And the answer, in fact, is true. And we show that there exists a 0.505 competitive algorithm for online bipartite matching with reusable resources. And now I'm going to explain our algorithm. Our algorithm is similar to the two-choice algorithms recently studied in the literature of the matching, and it has two main parts. The first part is the outer algorithm, and it always maintains an online feasible primal dual solution to the problem. And upon arrival on online vertex J, the outer algorithm proposes a set Qj from the neighbors of J to the inner algorithm. And the set Qj has a size of at most 2. In the case that the set Qj is only one vertex, we call that run a deterministic run. And in that case, Qj only contains a single vertex I1. And otherwise, if Qj contains 2 vertices, for example, I1 and I2, we call that run a randomized run. And the inner algorithm receives the set of proposals Qj from the outer algorithm, and it has to pick a random vertex I from Qj, which is the set of proposal that is given to the inner algorithm. So it picks a random vertex I from Qj, and it adds I to the matching if I is available at that time. And also, an important property of our algorithm is that the outer algorithm does not look at the realizations of the random decisions of the inner algorithm. And it only knows the probability distribution about probability distributions of the matched vertices. For example, consider a simple randomized inner algorithm that upon receive a proposal Qj picks a vertex I in Qj uniformly at random. And suppose that this is our online graph, and a first online vertex arrives with 3 neighbors. And if the outer algorithm proposes 2 of them, the outer algorithm only knows that those 2 vertices are matched with probability of half. And it doesn't know the realization of the matching edge. So it knows that those 2 vertices are matched with probability of half, and also the online vertex gets matched with probability of 1 because all of its neighbors are available. And again, if we receive another online vertex, it updates the probabilities based on this and so on. And when the algorithm only proposes 1 edge for the offline side, we can say that that vertex gets matched with the probability of 1. Because if it is available, the algorithm adds it to the matching. And let delta mu ij be the probability that the inner algorithm matches the online vertex j to an offline rental vertex I, and let pij be the probability that I is available at the time j. So considering the simple randomized algorithm that I just mentioned, when we pick a vertex I uniformly at random, we can say that delta mu ij is 0 when I is not in Qj, because in that case, the algorithm doesn't match I. It is Pij when we have a deterministic run, in other words, when size of Qj is 1. And when we have a randomized run, the algorithm picks I with probability of half, and also I was available with probability of Pij. So we have delta mu ij is equal to Pij over 2. And the question is that can we get anything better than this and beat the half approximation for the problem? And we showed that we can do that by introducing negative correlations between the decisions of the algorithm. So in our algorithm, decision of every proposal set Qj depends on can be correlated based on the previous D sets that are proposed to the algorithm. So specifically, let J prime be the previous time in which I is proposed to the inner algorithm. And our gamma OCR or gamma online correlated rental algorithm guarantees that if J is larger than J minus D, in other words, if the last time I is proposed is within a window of size D, then the algorithm matches vertex I with the probability of Pij over 2 plus gamma times that number. And that number, which is Pij prime minus delta mu ij prime, is basically the probability that I was available at the time J prime, but it didn't get matched at that time. So intuitively, our algorithm implies that whenever a vertex is available and gets proposed to the inner OCR algorithm and it doesn't get matched, it has a slightly higher probability to get matched the next time it gets proposed to the algorithm. And we show that based on this definition of gamma OCR, there exists an 1 over 32 OCR online algorithm. And our algorithm is inspired by a recent FACS paper, which proposed a same kind of inner algorithm for the non-reusable case. They show that there exists an online correlated selection algorithm in which if an online vertex gets proposed to OCS for k times, it gets matched with probability of at least 1 minus 2 to the negative k times 1 minus gamma to the k minus 1. And that is slightly better than 1 minus 2 to the negative k, which is the algorithm that pick one of the vertices purely at random. And using that online correlated selection, they show that we can achieve 0.5086 competitive algorithm for online weighted matching with free disposal. So our algorithm is inspired by their work, and in our algorithm, every online run sends a small stochastic message to the next D-1 runs to ensure that we have a negative correlation in the decisions of the algorithm. Let Ij be the message that vertex I receives at the time J. In our algorithm, Ij is either unknown. In that case, we don't have a specific message for the vertex I, or it is selected, which shows that the previous time that I is proposed to the inner algorithm, it got selected by the inner algorithm, or it is not selected, which shows that the previous time that the vertex is proposed, it didn't get selected, and we will select it the next time that we see that vertex to have the negative correlation. So first, let's talk about the deterministic runs. Let a Qj be a deterministic run containing a single vertex I1. In that case, our algorithm resets the message for I1 and in a deterministic way selects the I1 as an output. Now consider randomized run Qj, which contains 2 vertices I1 and I2. A randomized round in our algorithm is a sender round with a probability of half. And in a sender round, we do the following. So we pick 2 numbers, L and M, uniformly at random. And we select the vertex IL as the result of the algorithm. However, we send the message for the vertex IM for the future runs. If M is equal to L, that means that the vertex M is selected by the algorithm and we send the message selected. And otherwise, we send the message not selected for that vertex. And our algorithm is a receiver run with also probability of half. In other words, a run is a sender with probability of half, and otherwise is a receiver. And in a receiver run, we draw a random number m from 1 and 2 uniformly as random. And im is a vertex that we want to receive the message. And if message for im was selected, to ensure that we have negative correlation, we don't select im in that run. And otherwise, if it was not selected, we surely select im in that run. And if the message for im was unknown, we pick one of the vertices in the proposal set uniformly at random. So as I discussed, our goal is to have a better probability that I gets matched whenever it gets proposed to the algorithm, but it doesn't get matched. And let J prime be the previous time that vertex I is proposed to the algorithm. That means that vertex Qj can send a small stochastic message to vertex Qj prime can send a stochastic message to Qj. However, we care about this message only when the vertex I was available at the time J prime, and that depends on the previous proposals to the algorithm and causes a lot of dependency. And the way that we analyze the algorithm is using a simple and yet very useful observation. And in that observation, we show the following. So let mu I q1 up to qj be the expected number of times that the algorithm matches vertex I. And based on this definition, we have that delta mu ij is basically mu of q1 up to qj minus mu of q1 up to qj minus 1. And in the observation that I mentioned, we show that the mu of q1 up to qj is basically the same as mu of qj minus 1 up to q1. That means that if
we are almost out of
that
time.
shows that if we reverse the sequence of the proposals, the algorithm matches the vertex I the same number of times. And using that property of the algorithm, I will go over the details, but we can actually calculate the probability that algorithm matches vertex I, and we get the following. You can find the detail in the paper. And based on this, we show that there exists a 1/32 OCR algorithm, and that algorithm leads to 0.505 competitive algorithm for the problem. So for the future work, the main important problem is whether we can achieve 1 minus 1 over E competitive algorithm for this problem. So right now, the best upper one is the same as the non-reusable case, and we don't know if we can achieve 1 minus 1 over E, and I believe we should be able to. And the other future direction is whether we can generalize our techniques to the asymmetric case, where each vertex becomes available after DI time steps. So the DI can be different for different vertices. And these are the important open questions. So we also have some sort of results for the second one. So if you are interested, I would be happy to talk later. Thank you so much.
Let's wrap things up.